Alright, here's our video today. How CO2, carbon dioxide, lets sunlight in, visible light, but stops heat, infrared light, from going out. So basically this video is how carbon dioxide warms the planet as it has warmed Venus. Alright, let's make this simple. And I should make it simple by having a pen available. So we should know that the sun, there's the sun, as you know, it's going to emit, not admit, but emit. It's going to emit electromagnetic radiation. And the electromagnetic radiation is just light. It's the light as photons, little packets of light. Now in the electromagnetic spectrum you have radio photons, radio waves. That's light, and that's the longest. So basically radio waves, they can go anywhere. They can go from 1 meter. They can go from 1 meter. They can go to kilometers. So they're the longest wavelength. And then of course microwaves are light. And then infrared, which we'll talk about in this video. Infrared is light. VL is visible light. That's light. It's the only light we see. UV is ultraviolet light, which we don't see, but some animals see it, some birds see it. And by the way, snakes can see infrared, and so can mosquitoes. It's basically heat. So this heat we're talking about is infrared. Okay, UV, and then we have X-ray. X-rays are light, and gamma is the shortest wavelength. So they have different wavelengths, they have different frequencies, and that's important for this video. So in simple terms, what happens here is when visible light enters our atmosphere, and again the sun emits mostly visible light and infrared light, mostly. It does emit all the others, but at small percentages compared to visible light. Now it also emits infrared in the near infrared range, whereas Earth will emit it back in the mid-range. We'll talk about that. So again, when this visible light, we'll talk about it in simpler terms, when visible light enters the atmosphere and it hits the ground, when it's absorbed by molecules in the air and the ground, that visible light will be turned into thermal energy. And that thermal energy is basically heat. And that heat is going to move back. It's going to go back in the atmosphere, try to get out into space, those photons, as infrared light, which is the heat. Now carbon dioxide, it has a special bond, and in that bond they have a special frequency they can accept. That is, they can accept a certain frequency that perfectly matches infrared. And that's how CO2 will absorb infrared. It doesn't absorb visible light, it absorbs infrared light. And that's why the planet can heat up. And here's the compound CO2. As you can see, it's CO2 because it has 2 oxygen, right? Carbon dioxide, di in science means having 2. And before we go into this a little more, we should know about the octet rule. I'll get my pen ready here. Write down the octet rule. The octet rule. Simple rule, not fancy. So as you can see, here's oxygen. Here's 1 row, and here's 2 rows. And the same goes with carbon. It has 1 row, 2 row. And we can call these rings, we can call them energy levels, we can call them orbits. This is a Bohr model, after Niels Bohr. So in the first energy level, or first ring, or first orbit, the max of electrons you can have, by the way, they are electrons, the protons are in the nucleus, right? So there's 2 electrons that oxygen has in the first row, and so does carbon. It has 2, because again, like I said, 2 is the max for the first, we'll call it the first ring, make it easy. But for the second ring, the second orbital, the second energy level, the max you can have is 8. So when you reach 8, you are complete. But oxygen doesn't have 8. It needs 2 more. So let's count them, right? We'll circle it. It's 1, 2, 3, 4, 5, 6. It has 6. it needs 2 more. And guess where it's getting it from? From carbon in the blue there. So the carbon right here is going to share this one, and now oxygen is complete. That's what they want to do. That's what atoms want to be. They want to be complete. You complete me, oxygen is saying. Now carbon, they want to be complete too. Carbon only has 4 on the second ring. Right? They have 1, 2, 3, 4. 3, 4. They need 4 more. And again, they're going to get them from 2 oxygen. Now they become complete. So it's all about getting 8 on the second ring. So once they're complete, there is a bond here, and we have a compound, CO2. CO, and that little subscript means we have 2 oxygen. Now, the bonds themselves, the compounds will wiggle. Everything moves in the universe, everything. Nothing stands still. So they will wiggle. But when a photon of light, remember, all light in the electromagnetic spectrum, they're photons. When a photon touches them, right, they will not just wiggle, they will dance. But it has to be at the right frequency. So we have to go back to the electromagnetic spectrum. All right? Here it is, the electromagnetic spectrum. And we blew up, and the picture is blown up, the visible light that we see. So again, I told you, radio wave is long. Radio waves can go kilometers, they can go miles. And gamma, let me get my pen working here. Gamma is extremely short and extremely dangerous, along with X-rays. So as you go from radio, as you head this way, the wavelengths, then the frequency, the wavelengths get shorter, but the frequency gets higher. Very important. And that higher frequency means higher energy. So in the infrared, and I'm just giving you a general range, it could be anywhere between, it could be like 0.75 micrometers, has this little fancy Greek letter mu, micrometers. Whereas if we get into the red range of visible light, red is the longest of visible light, and that range could be like 0.62 micrometers. Now, again, I told you the sun will emit infrared in the near range, about 0.75. The near infrared range. But the mid-range could be anywhere between 2.5. So the mid-range infrared that leaves the Earth, that's emitted from the Earth after the visible light is absorbed and turned into thermal energy, that mid-range infrared is the exact frequency that will make CO2 dance, so to speak. It's the extreme, it's precisely the right frequency. So what happens next? The CO2 absorbs the infrared photon. And again, there's millions of photons, billions of photons, billions of CO2 atoms. So, compounds. So what happens? Once it gets absorbed, it's only going to be for a fraction of a second. And then it's going to be released. And the photon will continue its journey. But the thing is, it's like a ping pong machine up there. It's like a demolition derby up there. Because every time it's released, it's being absorbed by something else. So the photon's on a journey. It's trying to get back into space. It's trying to move. But again, it's being bounced from different compounds of CO2. The more that's in the atmosphere, the longer it will take to get out into space. So you can see if we build up our atmosphere with CO2, those photons, those infrared photons, could stay longer. And again, what heats up the air is this movement, right? This movement, this bouncing, this absorption is creating kinetic energy. And kinetic energy obviously creates heat. All you have to do is just rub your hands together very hard, and you'll see that heat being created by friction. And by the way, when it's re-emitted from the CO2, it's going left, right, up, down, sideways. There's not just one straight path. And so it's like a demolition derby. Like I said before, it's just bouncing into so many compounds and atoms in the atmosphere. All these collisions is creating kinetic energy, like I said before, and that's creating heat. Now, how long does it stay before it does go into space? It's called its residence time. Let's write that down. So right over here, residence time. In other words, how long it stays before it finally escapes Earth. So right now, scientists are estimating that the average residence time of energy in the Earth's atmosphere for a photon right now is about 50 to 60 days. Let's write that down. As of now, it's 50 to 60 days. So the more CO2 that increases in the atmosphere, the longer that will be. So if you can think about this, think about this infrared photon trying to escape, and it's being hit all the time. It's being absorbed, hit, and it takes 50 days to finally, or more, 50 to 60 days or more, depending on where it goes, to finally get into space. And this only works with infrared at the mid-range level. So visible light has too much energy for CO2 to absorb it. And of course ultraviolet and X-ray and gamma have much more energy. But it has to be a precise frequency, and infrared has that precise frequency. So that's our video today.